October, November 2015, Physics, paper 42, question number 1A, 1A1. They're asking to show that the kinetic energy of a satellite is given by this particular expression. So before we go to proving this, we need to identify and understand that what provides the energy, or what is the force that provides the force required for this to go into orbit. That is provided by the centripetal force is provided by the gravitational force at that point. So in page 273 of your textbook, according to Newton's law of gravitation, we obtain the equation F equals G capital M simple M upon R squared. So that the force of gravitation is equal to the centripetal force. In our circular motion lesson, we get the centripetal force equation as mv squared upon r. So mv squared upon r, those are the two equations that we need to relate. So we have one equation that is the gravitational force gmm, because this is satellite, we put it as s, and the separation is x. They have given the radius is x, so the detail is there in the question. Then mass of the satellite v squared divided by, again the separation is x. So when we simplify this, this square to 1x gets cancelled out, masses gets cancelled out, then you are left with the equation v squared is equal to gm upon x, right? Gm upon x. But this is not our answer. They are asking for kinetic energy, right? So kinetic energy, what is the equation for kinetic energy? Kinetic energy is equal to half mv squared. Now because it is mass of the satellite, I will write it as that, mv squared. So now instead of v squared, we can substitute this gm upon x, right? Gm upon x. So let's do that. Let me delete this. So we have the equation kinetic energy is equal to half ms v squared. So instead of v squared, we can put gm upon x. So this results in us obtaining g capital M simple M s divided by 2x, right? So I hope you understood. If you have any doubts, please ask me, then I will explain it further. Then part 2 is state an expression in terms of g, m, ms and x for the potential energy EP of the satellite, right? So EP of the satellite. So now then for a point mass m, we have an equation. If you can't remember that, please look at page 276. You will understand that. Then you have the value for phi actually, negative gm upon r. The negative sign comes because it is from we are measuring from infinity, right? So this is for point mass, considering to the point mass. Then from away from the point mass, the satellite is away from the center of the earth, so it is away from there. Then the potential energy equation equation goes as EP equals negative g capital M simple ms divided by the separation is x. And this is the answer. So always remember, this negative sign is very, very important. If you do not have that, you are going to lose marks. This comes out of the potential energy, gravitational potential equation. I hope you understood. If you have any questions, please raise. Then part 3, using answers from 1 and 2, derive an expression for the total energy ET of the satellite. So ET is equal to kinetic energy plus potential energy. So the kinetic energy equation is, we got the kinetic energy to be Gmms upon 2x. Then to that we have to add because he add negative, because potential energy we got a negative answer, Gmms divided by x, right? So we have to simplify this. Now we have to get the common denominator, that is 2x. Gmms minus 2gmms, right? So the both of these are equal, therefore you are left with negative gmms upon 2x. That is the final answer. That's simple arithmetic. If you have difficulties, please ask. Part B, small resistive forces acting on the satellite causes the radius of its circular orbit to change. Small resistive forces acting on the satellite causes the radius of its circular orbit to change. Use your answers to state for the satellite A to state for the satellite whether each of the following quantities increases, decreases or remains constant. So the total energy, resistive forces acting means, so the it is having an effect on the force of total energy. So the total energy would decrease, right? Total energy will have to decrease because the resistive force acts against the centripetal force. Then the radius of the orbit, when the energy reduces, right? Energy reduces, what happens? It falls onto a lower orbit. It falls onto a lower orbit. Higher the energy, it will try to escape. And the potential energy also will reduce because it is getting further away from the infinity. Then what happens to the kinetic energy? Closer and closer it is to be in the orbit, it has to have a very high velocity. It has to go at a very high velocity closer to because the gravitational force is higher. As a result, that centripetal force is higher. As a result, it would have a very high velocity. So the kinetic energy is high. The fourth one, kinetic energy increases, all the other three decreases. I hope you understood the answers for this question.